Hello. So in this lecture, we are going to look at how laser oscillation itself take place. So we are looking at two aspects, essentially that of gain and a related aspect of loss that basically decides the threshold at which the laser operates. So let's look at the simplest of the models, and this is a little more sophisticated than the very superficial model that we discussed very early on in these set of lectures. So what I have essentially a plane wave traveling in one dimension. Uh, so we will try and not bring in all the details that we have learned about transverse modes, longitudinal modes, and so on. First, let us just focus on this process of simple amplification. That is, I have a medium, right? And it has got a collection of atoms. These are my active atoms, and this could be a gas, it could be a doped solid, whatever you would like. But at the moment, let's look at a gas. And this is my positive z direction along which my radiation is coming in. So I make a few assumptions. The first assumption is that it's a narrow band radiation, and individual atoms have got uh, a resonant transition whose frequency is nu2 1, and my incoming radiation has got a frequency nu, and the narrowband frequency is such that nu is very close to nu2 1. That's we are near resonant condition. So the first step in a laser is basically this business of amplification. So when does amplification happen? It happens when the atom is such that there is population in the excited state and then the process of amplification, stimulated emission. So this notion of amplification, let's just consider the following situation. If I'm looking at this plane at Z, this plane has got a transverse area A, and if I'm asking what is the rate at which energy transfers through this plane at Z, so the rate of energy transfer can be given as the intensity, which is largely at the frequency nu, which is the incoming radiation at Z, multiplied by the area will give me the rate of energy transfer through A at Z. Absolutely similarly, I can write down a similar rate which is at the next plane. Imagine this is the plane at Z plus delta Z. I'm going to look at a limit of delta Z being small. So this would be the rate at which the energy is transferred through A again. The area A remains constant, but this is happening at Z plus delta Z. If I'm looking at the difference between the two, that is I nu at Z plus delta Z minus I nu at Z, this I can write down in the limit, of course, times A. This I can write down as a differential in Z, which is at Z times A times delta Z. And this is true in the limit that delta Z tends to 0, right? So this is essentially going to give me the rate at which the energy is leaving this volume clearly, right? So we are looking at the radiation, the rate at which energy is coming in, rate at which energy is going out, and the difference between the two is going to tell me the rate at which the energy is uh, leaving this volume. And let me just quickly remind you as a small aside, the relationship between energy density and intensity. So imagine that I have an intensity at Z I can write it as the energy density, electromagnetic energy density as Z multiplied by the velocity with which the radiation is propagating, right? So this is energy density and this is the velocity of propagation of the radiation. So if it's we are considering a very dilute gas, so essentially this V is in our situation is just C. If this quantity is simply the rate at which energy is leaving this volume, so I can write down that. So minus dou by dou T will give me the rate of energy density, which is the minus sign gives me that the energy is leaving this volume, and the volume is simply A times delta Z, and the total energy in that would be simply the energy density at Z times A times delta Z. This is the total energy. The negative sign gives me is leaving the volume, and this quantity should be equal to the above, which is dou by dou Z I nu Z times A delta Z. Now note in all this that my A is a constant. The delta Z is small, but it is a constant. It doesn't vary with time. So I can rewrite my U as simply I by C. So that would mean the relationship I get, I can rewrite this as minus dou by dou T um, I by C, which is I at Z, and given the fact that my A times delta Z is common on both sides, I at Z, right, times A delta Z, I can cancel these out, and essentially what I get is the following equation of continuity, if you like. That is, the energy stored within that volume is basically the rate of change in the energy in that volume is equal to the rate at which the energy is leaving that volume. So you have dou by dou T. This is similar to a one-dimensional uh, Poynting theorem in electromagnetics, but let us not worry about that part. Uh, it holds good for plane waves traveling in a particular direction, and here the direction of choice is Z. All right, so this is the important equation of continuity, and of course I could have got this equation uh, from Maxwell's equations as well, but this is a nice, a neat way of obtaining it by sheer arguments of related to energy balance. On my right hand side, there is a zero. That simply means that there is no loss of energy or a gain of energy within this slice delta z, where whatever comes in is what goes out, right? So now imagine that I had a medium which could, for example, uh, change the change the energy within that volume. I could have atoms which are all in the ground state, and then these will lead to absorption, and the electromagnetic energy would actually be lost within such a volume. Absolutely similarly, the energy density might increase in this volume if we had atoms which are prepared in the excited state because of stimulated emission. So given these two scenario, one can basically capture change in energy within this volume. So my operator is 1 by C dou by dou T. There is a dou by dou Z, and this operating on I nu is going to be, so the right hand side is no longer 0, but it can be written as, so recall sigma of nu was the cross section, sigma of nu times phi gave us the rate at which the population was changing, and this was proportional to n2 minus n1. Let us just look at it carefully. So if I have atoms sitting in the ground state, right? Remember that my ground state is level 1 and my excited state is level 2. So if I atom sitting in the ground state, that will lead to absorption. Hence on the right hand side, I will essentially get the rate at which population is decreasing, right? Because there's a negative sign. And similarly, if N2 is larger, I would get the rate at which population is increasing. And you know that the energy change is precisely equal to this times h nu, right? Because this part, the prefactors which I wrote is basically change in population, and this multiplied by energy is going to give me the rate of change of energy uh, within the region of which I'm considering. I can rewrite this in the following form. That is, my right hand side can be written as sigma nu I nu. Recall that again h nu times phi nu, which is the photon flux, which is photon per unit area per unit time times energy. So this will give me basically power per unit area, which is same as I nu. So this is aside. So this I can write it as simply I nu times sigma, which is a function of frequency, n2 minus n1 times simply I nu, right? So this people in different books, you would find that the sigma is related to either the stimulated emission, Einstein B coefficient, or the Einstein A coefficient, which we have seen in case of natural broadening earlier. So, you might find this formula written in a variety of ways. Let me just write a few of them. For example, it might be written in this form, h nu by c, where this is Einstein B coefficient between the states 2 and 1 that governs, stimulated emission. S of nu is the line shape times I nu. You might find in terms of, the Einstein A coefficient. Remember lambda square over 8 pi. This would be familiar to you, times A21, right? Times N2 minus. So let me invoke another detail. Uh, Let me write this as G2 by G1, where G2 and G1 are integers that capture the degeneracy of the particular state, and this is typical of atoms. So I will come to that just in a moment, but essentially, all of these formulas state exactly the same thing. And in the event that G2 and G1 are 1 or equal, then just turns out to be it's N2 minus N1. So succinctly, I can simply write this as sigma nu. I can write this as G2 by G1 N1 times I nu. So this prefactor, right? Let me identify it everywhere. This prefactor, these are all equivalent factors, and all these factors is what I identify as G nu, which I am identifying as a gain coefficient. So let me first, fix this notion of degeneracy. So G1 is and G2, these are related to the uh, level, the atomic level degeneracy. So, in atoms, for example, I'm looking at, you know, um, let's say rubidium atom, and rubidium has got D1 and D2 lines, or sodium atom, any of these atoms. So then what happens is that the ground state and the excited state are not merely just one state. So for example, I could have uh, three degenerate states. So for example, without going into too much detail of quantum mechanics, so if this was, imagine that this was the F equal to 1 state, right? Where F is the total quantum number, including the nuclear spin. So one has to add up, the total angular momentum arising out of orbit, the spin, and the nucleus, and you add them all up. And then, if imagine that this is the state corresponding to F equal to 1, then there will be uh, three different uh, three degenerate states, okay, which correspond to m equal to 0, m equal to plus, and m equal to minus 1. These are magnetic quantum numbers. And so, and imagine that my excited state was f equal to 0. So you see that, uh, so given a particular f, the amount of degeneracy is simply given by 2f plus 1. Right? So given such a scenario, now you see that in the ground state, so in this case, the G1 factor, right? Here G1 corresponds to the ground state. So G1 is 3 because there are three different states. And on the excited state, G2 is just uh, 1, right? So I'm calling this F1 and this is F2 corresponding to uh, the ground and excited state. And you see that the ground state population is distributed among three states, right? Because there are three equivalent states. You see that in the ground state the atom will be equally distributed, and a particular photon will couple a particular transition. For example, the photon couples to this transition. Then you are not really you are looking at the population inversion, which is against only one third of the population in the ground state. So for example, if I put these numbers into these equations, you see that my N2 uh, uh, G1 is 3. So my N2 minus N1 by 3 is what I'm going to deal with, right? So that is what is captured in this notion of level degeneracy. So yeah, let's not focus on too much on that. Let's assume that G1 and G2 are essentially 1. Um, just to keep the discussion simple. But in the end, what I have is this very basic equation that will govern the gain, which is dou by dou z plus 1 over c dou by dou t operating on I nu is simply g of nu I nu, right? That g of nu, you should understand that it contains both the notion of population, and it also contains the notion of the spectral dependence arising out of the cross section, right? So it is not frequency independent, it is large. This quantity g will be large my if I'm at resonance. As I go away from resonance, the detuning will take over and my interaction with the atom is going to decrease. Similarly, what matters is to get this number to be positive, right? For positive number, I have to ensure that N2 is larger than N1. So I'm assuming here that G1 and G2 equal to 1. So under that assumption, my N2 should be larger than N1. And in thermal equilibrium, let's say I don't have any preparation, then it will be naturally be negative because N1 will be larger than N2, right? The ground state, most of the atoms will be in the ground state, and hence this will be a term that will lead to absorption. And essentially, as the light propagates through this volume, it is going to decrease. It's going to lose its energy proportional to this gain coefficient. You can also think of the gain coefficient uh, as essentially the inverse of absorption coefficient. Absorption coefficient is the situation where N2, so if I simply take my gain coefficient, right, and if I set uh, N2 to 0, right, excited state atoms to 0, then you see that um, sigma nu times simply n with a minus sign. That's how it will turn out to be, because n2 is 0 and all the population is going to be in the ground state, and this quantity is essentially what we call as the absorption coefficient. right? So that's how we have defined it earlier. So you would see that the gain and absorption play a they are very close cousins, and they simply depend on what is the population distribution within the atom, and that dictates whether it's the gain coefficient going to be positive or negative, and what is going to dominate. Now clearly this is called the gain coefficient, and why is that? Let me quickly justify that. So imagine I am in steady state. What does it tell you? That if I am in steady state, that tells me that my dou by dou t of I nu is 0. It doesn't change in time, which simply implies that I can write down the following equation. My dou by dou z of I nu is going to be g of nu I nu, right? Clearly, I can write down my solution for such a equation, and what I would get is basically I nu at z, for example, is going to be I nu at 0 exponential g of nu times z, right? That's going to be the solution for the above equation. And clearly, it tells you that the intensity is going to grow exponentially with this coefficient g of nu as it propagates along z direction, right? So that is why it is called the gain coefficient, because it captures that exponential dependence. Now, it might appear to us that this g of nu is truly independent of the intensity, but it is not true. You will see that because n2 and n1 themselves are dependent on intensity, this g of nu is not really a gain coefficient that remains constant, but it actually in turn depends on intensity, and the gain sort of saturates. And we will come to that discussion later. But at the moment, let us understand what is the role played by such a coefficient. I just want to mention another small generalization. So, for example, if I look at the gain coefficient, right, and I am looking at the gain coefficient for, let's say, some solid medium which has got a refractive index. Imagine for crystals, doped crystals, etc. Right? There is a background refractive index which is not really one. So what do you do there? So what you do is, in the expression for g of nu, simply undertake the following: that you replace your lambda by n, right? Where n is the background refractive index. So if you do that, you will see that your gain coefficient g of nu simply takes the following form, that it simply becomes lambda square by 8 pi, and there is a n square now sitting here. A21 is of course there, and there is a s of nu, which is the line shape function. This basically captures for us the gain coefficient when you have a background refractive index which is different from that of vacuum. So we have introduced the gain coefficient, and we have seen how it depends on the population as well as the scattering coefficient. Now let's quickly go ahead and look at the notion of threshold, right? So for threshold, I need to consider the notion of loss, right? In a laser, the loss is not only coming from the active medium or the matrix, background matrix within which the active atoms are, due to scattering losses within the active medium and so on, but largely, even in the most idealized situation, the loss is coming out of the extraction of the laser light from the gain cavity. So we will have to consider, at least a simple form of the cavity with this amplifying active medium sitting within it, and see how what does this kind of a notion of a loss in this system determines for us the notion of a threshold above which lasing happens. So for the discussion on threshold, let us consider a mirror. So I'm representing the mirror in this fashion. The hash line shows the non-reflecting side, right? So intensity comes in, let's call it I, and there's a reflected intensity, let's call it some coefficient R times I. The transmitted intensity is T times I, and it is such that this mirror is not necessarily ideal in the sense that there might be a scattering loss associated with this mirror, in the sense that my energy conservation for the mirror is going to be R plus T plus S is 1. So R is the reflection coefficient, T is the transmission coefficient, and this is the scattering loss. And this could arise in two different ways. For example, the mirror itself could be absorbing, or uh, it could scatter the radiation in a non-lasing mode, and such losses also will be uh, accounted for in this small s, which accounts for the scattering loss. This is my model for individual mirrors. So what I'm doing the following. I'm saying that I have two mirrors, and within these two mirrors, I'm going to I'm going to have my the the gain medium is essentially fills, you know, this the region between these two mirrors completely fills. I So in this situation, what we consider is a laser cavity where there is a laser oscillation going on, and this laser oscillation, because of the partial reflectivity at one of the mirrors, there is a finite output that is transmitted. We are looking for a steady state operation of this laser. What that equivalently means is that we are demanding for a constant output, right? The output that doesn't change in time. That would mean that the intensity output is a constant in time. This is typically what we call as a CW laser, or a continuous wave laser. And after analysis of threshold, we will actually find out that threshold, even though it is called gain threshold, it is actually a measure of loss in the system, and that the cavity loss is completely characterized by this notion of threshold. I plus is the intensity that is traveling in the positive z direction, and I minus is the intensity traveling in the negative z direction. This is my z axis, and my first mirror is at a location z equal to 0. The second right hand side mirror is at z equal to L, right? So this is the situation. The mirror 1 is characterized by R1 plus T1 plus S1 equal to 1, right? Similarly, the mirror 2 is characterized by R2 plus T2 plus S2 equal to 1, right? So this is essentially the my model system, and now let us uh, look at what happens at these two boundaries. So for example, let's look at z equal to 0. One can clearly see the following, that my I plus, right, the radiation traveling in the positive direction at z equal to 0 is simply the reflection coefficient R1 times I minus at z equal to 0. The radiation coming in in the negative z direction is reflex off, and and becomes the radiation traveling in the positive z direction, and the amount of reflection is captured by this coefficient of reflectivity R1. Absolutely similarly, I can write down the relations that happen at z equal to L. At z equal to L, what you have is the I minus at z equal to L is simply R2 times I plus at z equal to L. Not just that, we have other very interesting relationships. That is the equation governing the propagation from z equal to 0 to z equal to L. So for example, if I write down that as d by dz of I plus is simply g of nu times I plus, right? Again, I am looking at, let's be very careful, my interest is in steady state. Steady state. So d by dt of all my quantities I knew, etc., are set to 0. Okay, so this is my equation governing the right propagating field, and you see that the relationship that this results in is simply I plus at z equal to L is simply I plus at z equal to 0 times exponential g of nu times z. For that matter, it is g of nu times L, right? So this is another relationship. Similarly, I can write down the relationship associated with the backward propagating field. So di of minus z, if you like, is of I minus is simply g of nu times I minus. So I can get rid of my negative sign and put a negative sign here, right? And again, the solution I get from this is can be, remember that my I new I minus at 0 is I plus I minus at L times exponential g of nu. This is L minus z. Right. This simply implies for us the following, that my I minus at 0 is simply the I minus at L times e to the power of g of nu times L. Right? So we have got these four relationships that we need to work with. So two of these are the relationships at the mirror, and two of these relationships are arising from propagation inside this medium. Right? So we will use these four relationships and do the following. So what I'm going to undertake now is this task. I begin at, let's say, this point at mirror number 1, right? And I go across and get reflected and come back to the same location. So I'm going to look at this round trip. I will follow the fields as they go around in a round trip and see what we get, right? So that is our task. So let's look at this round trip, and let's traverse the medium, this medium around it. All right. So let me probably number this. So let me call this location 1, this location 2. After reflection, I reach 3. Then from 3 to 4, I traverse, and 4 back to 1, I am back again to my location. So let me, so at location 1, what will I get? Essentially, I use the first relationship, that is my I plus at 0 is simply R1 times I minus at 0. Then I can write down my I minus at 0 in terms of I minus at L, right? So we know that I minus of 0 can be written as uh, I minus at L times exponential g of nu times L. So the first step happened between 1 and 4, and this is what has happened between 4 and the location 3. And I can rewrite again that my I minus at L, right, is related to the I plus at L, right? So which is R2 times I plus at L times exponential g of nu times L. So I can relate this as going from between the relation between 3 and 2. And now I am back to my last step, wherein I relate my I plus at L to I plus at 0, which I can write down as I plus at 0 times exponential g times L, and there is already exponential g of nu times L. So that is how you see that I can rewrite this. So this is going from essentially is from 2, I've gone back to 1. So you see, this is how I've gone in a round trip, and I can effectively write this total round trip result as the following. That's R1 times R2 times exponential 2 times g of nu times L, because we have gone through the length 2L as we go around, times I plus at 0. So you see that for example, I can consider that mirror 1 has got transmission which is 0, and mirror 2 has got transmission which is finite. So I would also get from this laser a lasing output, right? So that lasing output is already taking away energy here. So if I maintain on round trip, if I maintain that this factor provides basically unity, then I have maintained that my output remains also a constant. If this factor is smaller than unity, right, in terms of its magnitude, clearly you would see that on as the photon goes around multiple times, eventually it is going to die out because this factor is smaller. And on the other hand, if this factor is larger than unity, that would mean that the gain would increase and the output will keep on increasing as it goes through multiple round trips. So you can clearly see that this round trip coefficient that we got here, if this is equal to 1, that sort of sets the threshold below which a gain value which is below this number is going to actually lead to a decrease in the output. So if you want a steady state constant output, we require that this particular coefficient is equal to 1. So let us see what is the consequence of that. R1 times R2 exponential 2 g of nu L being equal to 1 simply implies that my g of nu, which is what I am defining as g threshold, is equal to 1 by 2L natural log of 1 by R1 R2, right? So This can be written down in various forms. This could be minus 1 over 2L log of R1, R2. Because remember, R1 and R2 are numbers which are going to be smaller than 1, right? So their logarithms will be a negative. And not just that, if R1, R2 is close to 1, which implies that I can write down R1, R2 as 1 minus x, right? Where x is small. Log of 1 minus x, right, which is log of R1, R2, is basically uh, going to have these terms, which is minus x for small values of x, minus x square by 2, x cube, and so on and so forth. So you see that if I just retain only the leading order term, then you see that indeed I can replace this 1 minus x, log of 1 minus x, to be simply minus x, right, which is same as 1 minus r1 r2, right? So I can write this out as the gain threshold is 1 by 2L 1 minus r1 r2, typically when the reflectivities are very high. So this is a very important quantity. Now remember another uh, important scenario. Imagine that my gain medium has got a length L which is smaller than the L, which is the cavity length. This is my cavity length and this is the gain medium length, right? They need not be equal. For example, I have a tube within which the gas is enclosed in the helium neon laser, and I could have mirrors which are going beyond the tube. So in that situation, my gain medium doesn't occupy the full length of the cavity, and hence if those are different, then you see that my G threshold is 1 over 2L, where L is now the gain medium length, and this is 1 minus R1, R2 for high reflecting mirrors. And the other generalization which I want to talk about is that I could have distributed loss. So my gain threshold will be a value which is larger than what I have just written, right? So this A here is simply the distributed loss within the cavity. So again, this A here is the distributed loss through the cavity. That is, it would be loss per unit length within the cavity. Remember that our gain itself was gain per unit length. So A is a distributed loss which is not accounted for, because all that we have accounted for until now in the first term is the losses at the mirror. But all the other losses could be accommodated within this term A, which is loss per unit length. One important point which I want to emphasize, that clearly, the gain threshold is giving you a measure of loss. It is not a measure of gain. What it is telling you is that that is the minimum level of gain beyond which lasing action can happen. Below this value of gain, the gain is going to shut down. And what determines that value is basically 1 minus R. By the way, 1 minus R, if you look at it in form of our energy conservation relationship, you will see that is simply T plus S. So imagine the scattering losses are less, then it is the transmission. 1 minus R is essentially largely dominated by transmission of light, which is the output. And hence, that loss determines my threshold. So I need to at least compensate for what I'm extracting from the gain medium in order to maintain a steady state output from a laser. So that is essentially what the main lesson of what we have done with this notion of a gain threshold.